Hi, my name is Joe Inslee. I'm the team lead for Viz Analysis at ALCF. With me today is the rest of the Viz team, Janet Knowles, Sylvia Rizzi, and Victor Medavizzi. So we're going to talk about visualization at ALCF. So, so here's a brief overview. We're going to touch kind of briefly on, talk about the resources that we have available, a little bit about tools and data formats, and then a little bit different than we've done in the past. We're going to spend the bulk of the time talking about a couple of success stories that we've had working with users, right? So just to kind of give you an idea of some of the problems, or not necessarily problems, but the campaigns that people were running and visualization that they wanted to be able to do, and how we interacted with them and enabled them. And so we'll talk about a couple of those types of stories, and then cover some information and examples of in situ visualization and analysis. And we'll explain more about what that entails in a bit. Right, so first a little bit about resources and tools and such. So you may have already used, I don't remember yet, but so Cooley is our Viz and analysis resource. It's a 126 node Viz cluster where each node has basically 2 processors with 6 cores each. NVIDIA, now a little old in the tooth here, but high-end graphics cards, and 384 gigs of RAM per node. So and then the next sort of relevant aspect of this is that from this slide is that it mounts all the main parallel file systems. So the Theta FS0 and Eagle and Grand are all accessible from Cooley. Right. So as you're performing your simulations and writing stuff out the disk, presumably you're using one of those file systems, so you can access that data directly from from Cooley, so you don't need to move it. The other thing I'll say is that we are in the process of acquiring our next Viz and analysis cluster. That's still a few months out, but that's in the pipeline. So a little bit about tools. So there's all sorts of tools for doing Viz and analysis. This is by no means comprehensive list. But in terms of applications, there's Visit and ParaView and Insight. Insight is a commercial tool, which we don't have installed here on our resources, but you should be aware of it. It's another tool that's out there. Visit and ParaView, I'll talk a little bit more about in the next slide. But those are installed on both Cooley and Theta. There's other tools, and those are more general purpose scientific Viz tools. VMD, PyMol, Vito are other tools that are available, and actually VMD and Vito are also installed on Cooley. Those are more domain specific, in particular for doing molecular dynamics type visualizations. Now, of course, there's APIs for doing visualization. There's the Visualization Toolkit, VTK, and then also ITK, which is for doing segmentation registration. We have some tools that leverage the GPU for accelerated performance, like VL3, which is homegrown shader-based volume rendering and particle rendering application that we've used, and you'll see some examples of that. And there's also analysis environments like MATLAB, Parallel R, and utilities like GNU Plot for generating plots, and ImageMagick for manipulating images, doing compositing and the sort like that. So a little more about PairView, Visit, VTK. So PairView and Visit are general purpose visualization applications, like I mentioned. So they're primarily, well, not necessarily primarily, but they are GUI based. So it is, you do use a user interface with it. It does have a client server model, right, which supports remote visualization, which is how we generally get access to it, right? So you run a server on a visualization cluster, and it's parallel distributed, supports parallel distributed computing and rendering. So you run on multiple nodes of the cluster, and then you connect via a lightweight client on your local desktop or laptop resource in order to do interactive visualization. And then it's also scriptable and extendable, so you can write plugins to extend its functionality, and scriptable. And the way we generally encourage people to use it is use it interactively in client server mode to load representative data or your final data if you're already on your simulation, and use that to set up your visualization pipeline. So apply filters and materials and colors and such, and camera views, lighting, all that sort of basic configuration things, and then you can save that as a script, as a Python script, and then run PairView or Visit in batch mode to then go off and render animations and such in batch, so you don't have to keep the client connected. Both of the tools are built largely on top of VTK. Like I mentioned, they're extendable, so you can write plugins for them in VTK. And they both have in situ capabilities, which again, we'll talk about in a bit, but is going to become more important as we continue moving to larger systems and soon with Aurora to be on the ground. VTK, on the other hand, is more of an API, a programming environment. It has additional capabilities. As I mentioned, the other tools are built largely on top of VTK, but of course doesn't expose everything that you're capable of doing in VTK. So VTK itself has additional capabilities, finer control. That also requires a bit more expertise. In some cases, you're using it to build custom applications. And then I won't dwell on this slide too long, but just to throw out there that both Visit and PairView support, again, this is not an exhaustive list, but a fairly large array of data file formats and types. And so that list is growing all the time. And as I mentioned, so the chances are that whatever you're using is already available, there's already a reader for it for PairView. If not, as I mentioned, it's extensible, so you could write your own as a plugin, for example, or convert to one of the formats that it already supports. All right, so to switch up a little bit, like I said, I'm going to talk a little bit about a number of stories of working with where we've collaborated and worked with some of our users. So this first one is looking at blood flow. So the motivation for this one is circulating tumor cells, or CTCs, are cells that are detached from a tumor in the body and enter the bloodstream. So once they're in the bloodstream, they can migrate to other regions of the body, which and lead to metastasis, which are cancerous growths that are at a distance from the primary site. And as cancer is one of the leading causes of mortality in the US, and metastasis accounts for up to 90% of cancer deaths. So obviously, there's great interest in understanding CTCs, both for diagnostic and for research purposes. And And so isolation of CTCs can lead to further insights in cancer research and ultimately better clinical outcomes. Right, so to capture the capture of the CDCs by the micropost relies on a number of properties in the system. Some of them are related more to the CDCs themselves. The density on the cell surface, deformability, as well as size. And then there's parameters related to the device itself. So the configuration of positioning and size of the posts, and the volume fraction of amount of red blood cells in the system is another. So in this case, in terms of the modeling, computational modeling relies on modeling both the fluid and the solid, as well as their interactions with each other. And so the fluid was modeled using Vidas-Boltzmann method, for which we leveraged Palabos as the software library used there. And here the streamlines show the path of that flow in the image. And then the red blood cells and the tumor cells, which are the red and green blobs you see there, membranes, those were calculated using the fine-grained molecular dynamics code implemented in LAMMPS. And then the two were coupled using a merged boundary layer method, and that was implemented by our collaborators. So there's a number of different studies, simulation studies that were performed. One set was focused on properties that affected the ability of the CDCs to adhere to the posts, in particular the impact of varying sizes of the CDC, as well as density of the ligand coating that was on them. And so understanding this behavior helps to qualify the overall performance of the device. Another set focused on the transport of the cells into the device, and the role that cell density played. So for example, in the bottom images here, you can see that we sort of trace, I don't know if you can see my mouse here, we trace the trajectory of one of these particular cells. And so this is showing the expected trajectory through the flow. But because of the density of the cells and collisions and such, the observed behavior is what we see on the image on the right with this blue dashed line. And so it actually ended up in a different location. And so one of the things that they're looking at is understanding how the effects of the density of the fluid, of the concentration of the blood cells impacts that. So this particular simulation actually was one some time ago. It's computed on Mira before it was retired. And for visualization, we used PairView in this case. So it's standard surface rendering for the cell data. And instantaneous streamlines were calculated using the fluid data. And then in this case, in order to improve the IO, it's much quicker the cell data is much smaller than the fluid data. So when they were doing their IO, they would not output them at the same rate. So they output the cells more frequently to save on IO time and on storage. And so in order to account for that, PairView has capability for doing interpolation between time steps. And so we used that in order to match up the fluid and the cell data so that they had the same interspacing. PairView also employs Osprey, which is an Intel part of the Intel API, one API toolkit for doing ray trace rendering. And so we leveraged that in this animation too. So here I'll play the animation that we produced for this project.
High-performance computational models enable scientists and engineers to study the complex transport behavior of circulating tumor cells in blood cell suspensions. These models provide better designs for microfluidic devices, such as micropost sizes, shapes, and separation distances, to isolate circulating tumor cells from patient blood samples. This initial view shows the system as a whole. Red blood cells are shown as red membranes, while circulating tumor cells, or CTCs, are shown as green membranes. The white cylinders are the microposts on which CTC adhesion is expected to occur. Fluid streamlines, which indicate the instantaneous flow directions, can be seen throughout the device. Isolating the circulating tumor cells enables improved visibility of their general motion through the device. These CTCs are intended to adhere to the micropost. However, in areas of high shear stress, adhesive forces between the CTC membrane and microposts are not strong enough to resist fluid drag force. Zooming in will help reveal the role of collisions within the device. CTCs with either no or low red blood cell volume fraction in the device will generally follow streamlines closely. However, as patient samples contain many red blood cells, collisions occur regularly. Following the flow gives a sense of just how tightly packed the cells are in the sample. Collisions between cells have been found to allow them to migrate between streamline paths, which increases the likelihood of CTCs contacting a micropost. To see when CTC's contact with the micropost might lead to adhesion events, a section of a micropost is separated into front and top views for improved visibility. One can easily see the divergence of flow streamlines at the front of the micropost. This divergence corresponds to a stagnation point in the fluid. Because shear rate approaches zero at this point, it is a good candidate for adhesion events to occur.
Okay, and with that, we're going to move on to our next story, which is relates to cosmology, and I'm going to turn things over to Silvio to lead that one.
Hello, thanks, Joe. This is Silvio Rizzi. I'm a computer scientist with the Argonne Leadership Computing Facility. And we're going to present our story here, working with a successful cosmology team. This is going to cover the hack computational code and our interaction with the Exasky project as part of the Exascale computing project. We have, as part of the science team, to tell us a little bit more about the science and the code, the runs. We have invited Adrian Pope, and he's gonna tell us in the next slide a little bit more about the code and the science.
Okay, can you hear me?
Yes, we can hear you.
Okay, great. Yeah, so I'm a computational scientist in the computational science division at Argonne, and I've been a developer of the hack cosmological n-body simulation code for over a decade. So in these first few slides, I'm just going to go over a little bit about what hack is, what it does, and talk a little bit about one of the main simulations that Silvio is going to show some visualizations for. So overall, what we do with the cosmological n-body code is we're basically trying to simulate gravity in an expanding universe. And it's important to start with gravity because that's what dominates, that's the dominant force on the largest scales in the universe. And it's actually a rather compact set of equations to solve. So it's the Poisson equations, which are all listed to the right. So that's basically what we're solving. And in order to solve these, we use n-body methods with mass tracer particles. And basically, we have a 60 phase space of positions, 3D positions and velocities for each particle. And n-body methods work really well for basically tracing the evolution of this structure. And in a basic sense, what happens is gravity causes things to clump together. And so what you get over time in an expanding universe is the large scale structures basically condense out of an initially pretty smooth distribution of matter. And so at the bottom, we have some frames of a relatively small volume over the course of the history of the universe, showing how structure condenses out of it. So next slide, please. So the code that we're focusing on here and the one I've worked on is called HACK. This is the hardware hybrid accelerated cosmology code. And it's a code that we've run on many different HPC systems, on many different architectures. And the main thing we're focusing on is trying to calculate gravity, the gravitational force, in an efficient and fast way. So the tricky part about gravity is it's infinite and unshielded. So you have to basically calculate the force of everything on everything. And to do the kind of simulations that we want to do, to compare with surveys and things, we need a huge dynamic range. So we want a force resolution of about 1 kiloparsec to see where things like galaxies will form. And we want to do this in a box that's 1 gigaparsec on its side in order to get a statistical sample of what kind of structures actually form for a given universe model. And so we basically in one dimension need 10 to 6 dynamic range. So how do we go about doing that? We use operator splitting methods. And basically there's two kinds of operators that we need. We need kicks, which are where we update the velocities but keep the position fixed. And we need streams where we update the positions of the particles based on the velocities. And in the kicks, this is where we calculate forces and force changes. And here we split up the computation into a long range and short range component. And so in the long range, we take the particles and deposit them on a global mesh or global grid. And we used fast Fourier transform Poisson solvers to solve for the long range gravitational force. And this gives us about 4 orders of magnitude of our force resolution because we can do 10,000 cubed FFTs. And then for short range, we actually do more direct particle-particle comparisons. And this is very flops intense. And this is where we need to really focus on what kind of architecture we're running on. And this is where we get the remaining 2 orders of magnitude. And so this is an approach that's used by several different cosmology codes. And I think what makes HACK sort of particularly the technology that's interesting from HACK is how we do this handover between the long range and short range in detail. And we wanted to keep the sort of particle and grid interaction fairly simple. So we actually use a very simple deposit scheme, which would normally be fairly noisy. But we do a lot of spectral work with the solver to reduce this noise and also to keep the handover quite compact. So the plot on the right shows the overall force, which is just 1 over r squared. And in blue, we see that the force that we can get from our spectral Poisson solver. And so at long ranges, it gets 1 over r squared very accurately. But as you start to get close to the grid scale, it's not getting the complete force. And what we've managed to do is have the long range force calculate everything correctly beyond about 3 grid units. And this is a very compact handover. And this means that we don't have to do a whole lot of work in the direct particle comparisons. We can basically get a lot of the force from the FFT. Next slide, please. And so I think we're going to focus some of the visualization on one particular large simulation that we ran with HACK called The Last Journey. And this is an extreme scale simulation that we ran on the Mira supercomputer system at Argonne several years ago. And so in terms of overall science goals, what we really want to do is we want to go out with telescopes and surveys and measure the growth and distribution of structures on the largest scale. So we want to go measure where galaxies are, how they group together into galaxy clusters, and then how those galaxy clusters are distributed in the universe. And what this allows us to do is sort of figure out what's in the universe, the amount of matter there is, the amount of dark energy, the amount of dark matter. And we can also put in different models for dark matter and dark energy to try to figure out what some of its physical properties are that would let us match the distribution of galaxies. And the reason that we need to start doing really detailed simulations is that the data is getting really good. So current and near future astronomical surveys, we're already measuring the positions of millions of galaxies, tens of millions, maybe even hundreds of millions, and we're going to get to sort of billions of galaxies very soon. And this means that when we're doing statistical measures of structure formation, we can get sort of percent and sub-percent level accurate measurements from the actual data. And so we end up needing very accurate simulations so that we can make some sort of meaning out of what kind of universe we're probably looking at. And on the right is a sort of successive zoom on this last journey simulation out from the entire survey, or the entire simulation box down to, you know, highlighting a cluster of galaxies. And it gives you some sense of what the dynamic range is. Next slide, please. And so technically what we did to run the simulation is we used about 400 million core hours on Mira over the last 6 months of the operation of the machine. And we used the hack code, and we had about 1.24 trillion particles tracing the mass distribution over the universe in cosmic time. And then an important thing that we were really testing with this, so running a very large, high resolution, high fidelity simulation. And we've been working very hard on moving a lot of our analysis pipeline into the simulation itself, so that we can basically run the first pass at analysis while we already had the data in memory, so that we don't have to put a lot of data on disk and reload it and reduce it later. So a lot of the outputs, we did the initial pass of doing sort of data analysis and data reduction while the simulation was running to reduce how much we output, but still be able to do all of the rich measurements and make visualizations. And so outputs from this simulation are basically being used to help plan some upcoming surveys, and also to start help with the analysis of the data from the surveys once data starts coming in. And so some of these are the dark energy spectroscopic instrument, the legacy survey of space and time, the LSST project upcoming, and then even some overlap with cosmic microwave background experiments and some space telescopes like the upcoming Sprites. And so that's it for my introduction.
Thank you, Adrian. So we like to show this kind of charts, and this comes from the Grunculator, a tool available at ALCF to just see the jobs running on a given machine. In this case, this is a snapshot from Mira, and it's actually showing a full machine run of the last journey simulation. Right? It's using the entire racks, and if you look at the bottom right, it's running on 49,000 nodes. So you will see a couple of this in this presentation, of this charts in this presentation. Next slide, please. So let's talk about the data that we received from the science team to visualize. The code is particle based, so essentially we get particles, raw particles representing the dark matter. For rank 0 specifically, we get a dump every time step. So you will see a lot of that. There's also, as Adrian mentioned, data that has been already analyzed. So we call that the halo particles. So those are a subset of the entire data set that we get also from the analysis part of the code. So we put all that together and visualize it with different tools. One is our own VO3 framework, and for that we convert the particles into a regular grid, essentially an XYZ arrangement, equally spaced, where we represented the density. So essentially count how many particles are in each bin, equally spaced in 3 dimensions. With that grid, we get a regular grid and visualize the data using a method called volume rendering, essentially casting rays and simulating the propagation of light in that, assigning materials to every different density. When we also want to use a different tool like peer review, we need to convert the data to the specific format that peer review will be able to digest. In that case, we get all particles and convert them to VTK format, which is actually a format that peer review understands well. And we assign different fields to those particles. So for example, when it's a halo, and it's the particle representing a halo, we have its mass and its size and things like that we can use to visualize different properties, right? So in the visualizations that will come next, you will see a number of these techniques applied together. And if we move to the next slide, please, we can play the animation that we created with this data. So you have a mention here to the science team, the entire science team at the time. And starting from the first time step, and the first time step is actually, you can actually see on the bottom left, this parameter Z represents the time step, or in science terms, it's a redshift. So when it gets to 0, it's actually present time. What you're seeing here is essentially a volume rendering with VL3 of the rank 0 data, which is a tiny portion of what we're seeing now, right? A subset of the data, still a tiny portion of the entire universe that we're simulating. So this is, again, a volume rendering of the data converted to a regular grid. And here you can see in orange, the high density regions. And this is the time step is paused. So it's actually taking a look at this box at a given time. And now we get back to the tiny box. And in this case, it's a different visualization technique. We're using something called point sprites, where we get the particles and represent them as points that accumulate in the frame buffer. So that gives us all the dynamic range that the science team wants to look at. So you can see individual particles there, how they accumulate to create high density regions. And now the time is evolving, and we got to the final step of the simulation. Again, this is a tiny portion, a single rank of those many ranks that we're running, but now we transition to the full volume. That's what we're saying here is a representation of the full volume, the entire universe simulated. And now this is represented, this is actually rendered with peer review, and you can see the combination of techniques here, spheres that represent the halos, combined with volume rendering and particle rendering. So that gives us some of the structure and also helps highlight some of the filament structure, the filament structure that is generated when the simulation progresses. And now we're actually looking at a small region that contains the largest halo. Again, it's in the largest halo is in the center, and it's represented as a sphere. And you can see that its radius is larger than the others because we're scaling the sphere glyphs according to their size. And so this was an overview of some of the work we've done with this specific science team. And with this, I think we'll transition to another story.
Sorry, it took me a second to find my unmute. Thanks, Silvio and Adrian. So now we're going to switch gears and talk about a third case, which involves combustion. And for that, I'm going to invite Samuel Patel to introduce himself and tell us about his. So this was his project that we worked on with him. So I'll let him tell more about it.
Thanks, Joe. Can you hear me?
Yep.
Okay, great. So hi, everyone. My name is Samuel Patel. I am also in the computational science division. I work mostly on CFD simulations using systems like Theta and Theta GPU. And so one such simulation was this combustion problem. Well, the flow inside of an internal combustion engine. And this slide in particular shows the experimental setup, which was at the University of Michigan. And the image on the right is the computational work that we did for just a specific portion of that, which represents a specific portion of that experiment. So my colleagues and I in the Energy Systems Division at A&L wanted to understand some common turbulent modes or features that appear during a full cycle of the engine operation. And this was needed to help us understand how such features impact cycle-to-cycle variability during normal engine operation, which commonly occurs in typical passenger vehicles. And so the simulation that we did was actually a large eddy simulation. Namely, it's showing the simulation inside the intake, the exhaust port, as well as the cylindrical combustion chamber. And to do the simulation, we used a popular code called NEC 5000 and ran the calculation on Theta using around 500 nodes of Theta. And we ran the code for about 25 cycles of engine operation. And so in each cycle, there's around 720 crank angle degrees, which is a kind of a non-dimensional unit of time that measures the periodicity of this engine. And we were dumping data roughly every half crank angle degree. And so, and each file was around 10 to 15 gigabytes big. So we were definitely generating a lot of data for the simulation. And what we did with the data was, we needed some visualizations to help us understand some of the turbulent interactions, but we wanted to understand them in a variety of different ways. In particular, the visualization here helped us gain insight on how the large scale tumble and swirl vortices, which are common in engines, evolved throughout the cycle. In addition, we could see how the fast moving intake jet interacts with the cylinder walls to create a vortex waterfall, if you will. And ultimately, we needed to better understand the conditions just before top dead center, which here is at the end of the compression stroke, which is when the piston comes all the way up closer towards that red spark plug feature that you see in the image on the right. And so in typical car engines, this is top dead center is when the car or the spark ignites the fuel air mixture, and that propels the piston down, which generates power to turn the wheels and move your car. So the visualization here helped us view the interaction of turbulent structures in and around the spark, which can be hard to see in kind of lab used optical instruments. And so I just want to say as a final note here, these results really were crucial and beneficial for us because they helped us garner an Insight 2021 award to help further investigate the turbulence in other engine designs that are a little bit different from the ones that we studied here. So yeah, next slide, Joe. That's it for me on this slide.
Right, so Thanks, Samuel. So one of the other aspects was that we wanted to, in addition to just, focusing on the science data, which you saw on that previous slide, in order to be able to better tell and explain the science to a more broad audience, we wanted to provide context, right? And so for that, we wanted to see if we could integrate more production quality 3D modeling, visual effects software with our standard visualization applications. So use these tools, these more commercial tools that are traditionally used in film industry to help set the context for this science data. So we combined, so we use PairView, which we've talked about a little bit already, right? Scientific data visualization tool to help take all the NEC 5000 data, turn it into representations like things that you've seen, and create the geometry from that, and then combine that with Maya, which is a modeling animation software that's widely again used in the film industry, and then also V-Ray, which is a high-end renderer that can be used in combination with Maya. And so for this project, we actually leveraged the use of we had a number of students that contributed greatly to this effort to sort of figure out the pipeline for moving all these pieces around. And then once we do that, we're now looking to sort of standardize that pipeline and be able to apply it to a much broader set of science problems. But so here's essentially the way this sort of pipeline evolved is that, and I'm glossing over lots of the details here, including the exploration part, because that's always an important aspect of loading your data in and trying to understand where is it that the thing that you're interested in, and how do you turn that into visualizations and such. And so kind of glossing over that a little bit, and just to say that we used PairView to do the visualization. So once we applied our filters and figured out that pipeline, we exported all that geometry for a couple, few hundred time steps, few thousand time steps, and then used a V-Ray utility to convert that data into a format called a V-Ray mesh, which then can be loaded into Maya and used to combine that with other data. Now, because the volume of data was huge, as Samuel said, each time step was, I forget how big you said, hundreds of gigabytes or something. We don't want to have to move, and there can be thousands of time steps, petabytes of data. We don't want to move that from the file system on the parallel file system on the supercomputer. So we would transfer just a handful of time steps to a local workstation that we can then load into the. So Maya is largely an interactive, GUI-based application, and so we would transfer just a handful of time steps to a local workstation and load those in, and then apply materials and modeling and lighting, add colors to the scientific data that came along with it, in order to combine those into a final polished image. And then we can export that from Maya as a V-Ray scene. And then we can take that scene, move it back to the visualization cluster, where we can now use that V-Ray scene, which doesn't include the actual geometry of the data, but rather a pointer to where that data lives on disk, then which allows us to then swap that pointer out to point to different time steps, where we can then run this pipeline, run the V-Ray rendering part across multiple nodes of the cluster and render in parallel, and speed things up. And so by completing this pipeline, we were able to leverage the cluster, the Cooley, for doing all the heavy lifting, right? Making use of multiple nodes for doing the rendering, did all the computation there. And we didn't have to move terabytes of data across, what is likely to be low bandwidth networks to my local workstation where I'm going to do this modeling aspect of it. And so with that, I'll show the animation that we ended up producing using this
Automobiles
pipeline.
continue to rely on internal combustion engines, or ICEs. As fuel characteristics change, improving ICE efficiency is critical to consumer needs. Understanding how turbulence affects the efficiency helps researchers design better engines. In the physical lab, experiments of motored or gas exchange engine operations are often performed. This means there is no combustion occurring. Instead, the turbulent characteristics of the working fluid during engine operation are investigated. One such experiment is the transparent combustion chamber, or TCC3. To further study this turbulent behavior, computer models are generated and high-performance computing simulations are performed. The TCC3 engine apparatus consists of the intake plenum, the intake runner and port, a single-cylinder combustion chamber, the exhaust runner and port, and finally, the exhaust plenum. Simulation focuses on the combustion chamber and provides unprecedented detail of the turbulent flow during the engine cycle, which cannot otherwise be seen using experimental techniques. Simulation does not include ignition from the spark plug. Flow around this region is a critical component to understand the turbulent behavior in these types of engines. The working fluids, typically air, operate in an engine cycle which consists of a number of sequential and interrelated sections, or strokes. 1. Intake. 2. Compression. 3. Expansion. And finally 4. Exhaust. Time in simulations like these is measured in crank angle degrees, or CAD, as shown in the lower right. This indicates the angle of the crank which turns and moves the piston up and down in the chamber. During the intake stroke, atmospheric air enters the cylindrical chamber as the valve opens. The air quickly becomes turbulent. Despite the chaotic motion, the intake port and valve are carefully designed to produce large-scale, organized motion known as swirl, which helps maintain optimal engine efficiency. Focusing on the spark region from one cycle to the next, we see that the jet can impinge on the spark at different times. Here, for example, the vorticity contours with the high velocity reach the spark plug at slightly different points in time between these two consecutive cycles. The interaction of the fast-moving intake jet with the spark plug enhances the level of turbulence in the chamber. We see smaller turbulent structures early in the stroke, while later these structures appear larger. This seems to match our theoretical understanding of the fluid, where faster turbulence has smaller vortices and slower turbulence has larger ones. The intake stroke terminates with the closure of the inlet valves, establishing the conditions for the compression stroke. During the compression stroke, the valves are completely closed as the piston moves up towards the top of the cylinder. This compresses the air trapped from the intake stroke and increases the turbulent intensity of the air. Compression is followed by the expansion stroke, where the piston moves downward, which increases the volume of the chamber. Here, a sharp suppression of turbulent kinetic energy reduces the appearance of vortex structures. The final portion of the cycle is the exhaust stroke, where the exhaust valve opens, letting pressurized air enter into the chamber. As the piston moves up, air is expelled from the chamber through the exhaust port and onto the exhaust plenum.
So with that, we'll move on to our next portion, where we're going to talk about, this is some work in progress, where we start looking at doing in situ visualization and analysis. And in the first case, we were looking at the same problem. And I'm going to turn things over to Victor to talk about that.
Thank you, Joe. Hi, my name is Victor. I'm a computer scientist at ALCF. I'm in Joe's team. So one of the challenges that we have with supercomputers is the fact that I/O is much slower than processing and compute, and that this challenge and problem will only become worse as we move towards exascale. So this image has been created by Ken Moreland, one of our collaborators, and what it basically shows is the fact that as you move from computing, so running the simulation to memory, the speed is being reduced by a factor of 2. And then as you move the data from your memory to the interconnect, then again, there is a speed reduction of 2. And then from the interconnect to the storage, so saving into the disk, you have one more order of magnitude reduction. So in total, 5 orders of magnitude. So what that means is that running the simulation, it's a lot faster than writing or reading to the disk. And in order to solve this problem, one of the things that we are working on, and it's a team from other labs as well, we're looking into in situ methodologies and frameworks. More specifically, this is Sensei as an example. And what Sensei does is that if you have a simulation code, you can instrument it with Sensei, which is a framework, and now you get the in situ capabilities. So in situ means that instead of doing the data moving and copying the data from the simulation to the disk and then having to read that back, you will do the processing or analysis or rendering as the simulation runs, so in situ. Sensei right now supports a lot of adapters. To give an example, let's say you're writing your simulation code, you have a collaborator, and you want to share the data with them. And they have an analysis tool, and that analysis tool uses HDF5. Now they're going to come back to you and they're going to say, well, you know, can you give us HDF5 files? Now you would have to go to your code, add the HDF5 capabilities, and then rerun your simulation, have the HDF5 files, give it to them. Same thing, you know, maybe you have another collaborator, maybe they have ADIOS too. Maybe you want to work with the visualization team. We would prefer if you give us VTK files. So with Sensei, you instrument once, and just by adding an XML file, you can change the output. You can change to HDF5, ADIOS 2, or VTK, or some of the other adapters. Additionally, this is just for saving files, but you can also do in situ. So you can do something like Catalyst or libsim, where as the simulation is running, then it will do the rendering, and you will avoid that IO time. Additionally, one last thing that we're working on is in transit, meaning that even if you do in situ, that's kind of like a blocking call, meaning that the simulation is running and then it will pass the data with zero copy, so through the memory to, let's say, Catalyst for rendering. And what's going to happen is the simulation needs to wait for the rendering to finish. And maybe you don't want that. You don't want to block your code. So what you could do is you can use the in-transit capabilities, where you have either a few nodes on the same supercomputer or a few nodes on another supercomputer that will do only the rendering. So you run the simulation and the data will move in transit to the other nodes or the other supercomputer where you're going to do the rendering. Next slide, please. And we used Sensei to kind of evaluate and see what we could do with it, whether it scales or not for NEC 5000 and NEC-RS. Samuel has already talked about NEC 5000. The video Joe showed was simulated using NEC 5000. So it's a computational fluid dynamic code that simulates laminar, transitional, and turbulent, incompressible, or low Mach number flows. And NEC-RS is the next generation of NEC 5000 that can can also use GPUs, basically. What we have done is we have instrumented these codes with Sensei, and we have showed that we can run the codes at scale, more specifically 4096 data nodes, and we can generate those renderings in situ. Before instrumenting the codes with Sensei, I remember I ran the simulation and I saved every frame, and just with one run, I filled an entire allocation of 60 terabytes, just with one run. And now with Sensei, every image is just a few megabytes, so every frame. So that immediately saved me a lot of storage. on the supercomputer. And additionally, we have also showed that we can do in transit with ADIOS 2. You can see at the bottom image, we have the simulation running on Theta, and then using ADIOS 2, we transferred the data to Cooley, and we did the rendering on Cooley. And as you can see, it's 512 ranks doing the simulation and 96 ranks doing the rendering. So the numbers, you can do m times n. They don't have to be the same number. So the data will be reduced and will be transmitted on a smaller number of nodes. Next slide, please. And these are two example images that have been rendered in situ. On the left side, you can see a swirling turbulent air during the compression stroke of an internal combustion engine. So that has been rendered in situ by avoiding I/O. And on the right side, you can see NEC-RS, and this is an eddy simulation. And next slide. And Silvia showed an image with Mira running on a full machine. This is an image of NEC 5000 with Sensei running on almost a full machine, 4,096 nodes. And next slide.
So are you covering that or am I covering this?
You can talk about it.
Okay, so going back, so following on with what Victor was talking about with adding Sensei to simulation, if you think back to the first example I showed with the blood flow, this is that simulation. So we worked with some students to help instrument that coupled code. And so the way this process works is, right, so after instrumenting with Sensei, we run a small simulation case with Sensei. And as Victor said, in addition to being able to save, once it's instrumented, you can use different backends. And so we used a post hoc IO adapter, which allowed us to save out simulation data from this small run. And then using that data, we were able to then visualize that data using peer review, define our pipeline, save that as a Catalyst script. So Catalyst is the in situ backend for peer review. And then with that script, we were then able to then run the full scale simulation with Catalyst enabled using this Catalyst script and do visualization again in situ. So, oops, sorry, wrong way. And so this is an example of the results of that. And in this case, this is a small scale example, but you can see the different colors represented in the red blood cells. And so that's just to illustrate the distribution of the data across the ranks of the simulation. In this case, we were doing in situ, so the simulation and the visualization were both using the same ranks, same number of ranks. And so with that, we'll kind of wrap it up. And just end with saying that if you're in need of visualization help as you're running your campaigns, our team is available to help. Contact us through support@ALCF. And these are some of the things that we've worked on. We've done a number of covers for various publications and such, helped users do animations for example, the SC's visualization showcase, as well as the APS Division of Fluid Dynamics Gallery, and things along those lines. And of course, the in situ visit analysis, which is becoming even more important as Aurora starts to come online. And so with that, we'll wrap up and take any questions.